The last thing that we want to look at in today's lecture are the ideas of refrigerators and heat pumps. And again, what we will do, just like we looked at heat engines, we will take a look at the definition of efficiency for these devices. So in this course, we will be looking at, later on, refrigerators and heat pumps. Now, we'd said that a heat engine was a device that takes heat from a high temperature source, generates work, and rejects the waste heat to some other sink. The refrigerator and heat pump are basically the exact opposite. So these are devices that take heat from a low temperature and move it to a hotter temperature medium. So schematically, just like we did before, we looked at the heat engine. What we'll do now is we'll sketch out the heat pump. So for a heat pump, I'll put it here in a circle. And we're putting energy in, or work in, so we have some net work coming in. And then down at the bottom we have a sink, which is at a low temperature, and heat is flowing from the sink, and it's flowing up to a source, which is a high temperature source. And then here we have heat going up to the source. So it's going in the opposite direction that we saw for the heat engine earlier. Now, in terms of a schematic of a cycle, we would have a condenser whereby our working fluid is rejecting heat. Before that in the process, what we would have is a compressor. So the fluid is coming out of the compressor and flowing into the condenser. And here is where we do our net work in. We have an evaporator, and that's where the low temperature heat source is coming in. And then after the condenser, we come out, and here we have an expansion valve or a throttling valve where we lower the pressure. So if you recall the lecture where I was talking about the uniform flow process, and I showed you a video of air coming out of a compressed tank, we saw water and we also saw ice. That's essentially what was going on there, was this type of cycle. We had a compressor, it goes into a tank, it's hotter than the environment, so it rejects heat to the environment. I then open a valve very quickly, it expands, it gets cold, and when it's cold, that's when you can absorb heat from the surrounding environment. So depending on the particular application that you're looking at here, if the location where the heat was coming from, so your sink was the outside, that would be an example of a heat pump. If you've ever stayed in a hotel or a motel where they have an air conditioning unit in the window, they can flip the switch from cool to heat. That's basically a heat pump there. They're less common in Canada than they are in the United States. And if it is food, then that would be a refrigerator. So that is the idea of a refrigeration cycle and a heat pump. Now, in terms of the efficiency of this cycle, work net in is equal to QH minus QL. That is an expression that we will now use to determine or quantify how well the cycle is working. Now, for a heat engine, we talked about the efficiency, the thermal efficiency of the cycle. For a heat pump or a refrigerator, what we'll be talking about is the coefficient of performance. And this is written out in terms of a capital COP. And what it is our desired output divided by the required input. So looking at a refrigerator, we would have the coefficient of performance of a refrigerator. I'll write it as COP subscript capital R. QL is the desired, and the required input is the work that we have to do, which we could then rewrite that as so that becomes an expression for the coefficient of performance of a refrigerator, and similarly for a heat pump, so we can substitute for the network N using QH minus QL, and rearranging that, what we obtain is this expression. So you see it's a little different depending if you're dealing with either a refrigerator or a heat pump. Typically, values that you'll find for coefficient of performance of heat pumps, they're going to be on the range of 2 to 3, and it would depend upon the working fluid and the design of the system. Just like heat engines have different efficiencies, you'll find a variety of different efficiencies or coefficients of performance for heat engines. So looking at this in terms of a process diagram, so sketching it out again, we had our condenser. Now writing it in terms of a TS diagram, what I'll do is map the state information to a TS diagram, or sorry, TV. So with this process, we start over here at 1, typically. We go into a compressor, and so in the compression process, we increase in temperature, and that takes us up to state 2. Once we're in state 2, and in here we're doing work, so we have work coming in, Once we're at state 2, usually we're at a hotter temperature than our surrounding environment, and so we reject heat to the surrounding environment, or we heat in the case of a heat pump. So we're moving in this direction now, and let's assume that we end at the compressed liquid line, so that would be at point 3. We then go into a throttling valve, and a throttling valve is actually a constant enthalpy process, but it will bring us down something like that to state 4. And now we are at a lower temperature, and consequently what we're able to do is absorb heat through this process here. So that's what's going on within the evaporator. So that's mapping it to a TV diagram. Final thing that I want to say, we looked at the Kelvin-Planck statement when we were looking at heat pumps. Now we're going to look at the Clausius statement. And what the Clausius statement says is that no device can transfer heat from a cooler body to a warmer one without leaving an effect on the surroundings. And that effect would be the work that you have to do on the process. So you need to do work in order to move heat from the cold to the hot, which is the opposite way that we would normally see heat flowing. So we're in a way defying nature by doing this, but we have a cycle that enables us to do it. So that concludes this lecture. What we'll be doing next class is we'll be looking at the definition of a reversible process, as well as we will be taking a look at the Carnot cycle, which is the cycle that has the highest possible efficiency that you could have for a heat engine. So thank you very much. Bye-bye.